Hello everybody, welcome to Guidancee Education channel. We will see the topic that is discussed in this video. We are continuing class 11 chemistry, classification of elements and periodicity of properties. Periodic properties part 2, types of atomic radii. Please watch the video completely without skipping, and if you think the video is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. Also press the bell button and all button for notification of more videos like this. Thank you very much. Come, let us start the class right away. This is part 2 of periodic properties, types of atomic radii. In the previous video, we have seen that it is very difficult to estimate the atomic radius, and scientists have their own techniques to estimate the same. They resort to X-ray and spectroscopic methods. Three types of atomic radii are used. First one, covalent radius. Second one, van der Waals radius. And third one, metallic radius. What is covalent radius? I'll make it clear using this diagram. Here you see two atoms linked by covalent bond. There is clear overlapping of the orbitals of the two atoms. This is the distance between the internuclei, that is the nuclei of the two atoms, from the center of the nucleus of one atom to the center of the nucleus of the other atom. Half of this distance is the covalent radius, that is this much portion. For example, in hydrogen molecule, the internuclear distance is 74 picometer, that is 0.74 angstrom. Then the covalent radius will be half of 74 picometer, that is 37 picometer or 0.37 angstrom. In the case of chlorine molecule, the internuclear distance is 198 picometer, that is 1.98 angstrom. Then the covalent radius becomes 198 divided by 2, that is 99 picometer, which is 0.99 angstrom. So the definition of covalent radius is, it is half the distance between the nuclei of the same elements bonded covalently. Now we will pass on to the second type of radius, van der Waals radius. For that we will use the diagram that is shown there. Boundary diagrams for two chlorine molecules which are lying close by are shown here. The internuclear distance between two atoms belonging to the two molecules that lie close by is first assessed or measured. Half of this distance is the van der Waals radius. In the case of chlorine, this internuclear distance of adjacent atoms of the adjacent molecule is found to be 360 picometer, which is equal to 3.6 angstrom. Then the van der Waals radius is equal to 360 divided by 2, equal to 180 picometer or 1.8 angstrom. Now, let us define van der Waals radius. It is defined as half the distance between the nuclei of two identical atoms belonging to two neighboring molecules of an element in the solid state. Please make a note that the distance is considered in the solid state, because in the liquid state and gaseous state the distance will be more. Now if you compare the van der Waals radius and covalent radius of chlorine atom, you can easily understand that van der Waals radius is greater than covalent radius. This is true for all elements. Why is van der Waals radius greater than covalent radius for any element? This is because in covalent radius the atoms are bonded by covalent bond. There is overlapping of atomic orbitals. So the nuclei of the two atoms tend to be closer. But in the case of van der Waals radius, the van der Waals force which binds the molecules together in a substance is very weak, and there is a small gap between the molecules in a substance. So the nuclei of adjacent atoms present in adjacent molecules will be slightly apart when compared with that of the nucleus in the case of covalently bonded atoms. Therefore, naturally, van der Waals radius is greater than covalent radius. Now we will proceed to see metallic radius. In order to understand metallic radius, we have to first understand metallic bond. Perhaps you are already aware of this. Metallic bond is a bond which keeps the atoms of a metal together in a piece of metal. What is special about this bond? This is a diagrammatic representation of how the atoms remain in a piece of metal. The atoms are present in the form of ions. You see so many positive ions among a large number of free electrons, or a number of positive ions in a sea of electrons. The valence electrons from all these atoms have become free or mobile and exist in the form of these free mobile electrons. This is the electron sea model of metal lattice. Lattice means the three-dimensional arrangement of the particles. This is only a diagrammatic representation of this metal lattice. There is force of attraction between these mobile electrons and these positive ions, which keep these ions or atoms together. The force of attraction between the mobile electrons and the ion kernel is called metallic bond. Kernel means the inner part. So you should actually imagine the positive ions as inside the material and all the electrons flowing all around on the surface. What is metallic radius? Half the internuclear distance of two adjacent ions in a metallic substance is what you call the metallic radius. So when you give the definition, it is half the distance between the nuclei of two adjacent ions in the metal lattice. The metallic radius is always longer than covalent radius. See a few examples. For element sodium, metallic radius is 186 picometer and the covalent radius is 154 picometer. For potassium, it is 231 picometer and 203 picometer. For copper, it is 128 picometer and covalent radius is 117 picometer. What is the reason for the metallic radius being bigger than or longer than the covalent radius? This is because in the metallic radius, the mobile electrons are moving freely and their force of attraction is less. In the case of covalent radius, the shared pair of electrons are strongly attracted by the nucleus, so the force of attraction is more. This makes the covalent radius smaller or shorter than the metallic radius. I hope these points are quite clear. When we compare the length of all the three radii, we see that van der Waals radius is the longest. Then comes the metallic radius and then the covalent radius. So the covalent radius is the shortest of all the three. We will discuss the trend of atomic radius in the next video. I hope this video was of great use to you. If you think it is useful, do like the video, share the video with your friends and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. Thank you very much. We will meet in the next video. Until then, bye. Take care.